Potential energy comes in many varieties. This is a video about potential energy examples. Okay, now we said the major forms of potential energy were going to be gravity, big and small, and springs. So I want to do one example of each of those cases. This is just about finding the potential energy, so this video is going to feel really short and like it's just sort of the first half of a problem, because it is. Let's do this though. Let's say we have the ground here, we've got a ball, mass of 2 kilograms. We're going to put this thing, let's say 10 meters up, and we want to find the potential energy. Our potential energy requires us to have a location that we call h equals 0. I'm going to call the ground h equals 0. So my potential energy is mgh, 2 kilograms, 10 meters per second squared. 10 meters, 10 times 10 is 100, times 2 is 200, we get 200, and the units of this thing are joules. Maybe we want to say how much has potential energy changed when this drops from 10 meters down to 4 meters. So I'm going to find the potential energy at 4 meters. I'm going to get my 2 kilograms, 10 meters per second squared. 4 meters. 2 times 4 is 8, times 10 is 80. So the change in my potential energy is PE final minus PE initial is 80 minus 200 is negative 120 joules. This is a negative number because my potential energy, which depends on height, decreases as I get closer to the ground. So that's one form of gravitational potential energy, and this is honestly the form you're going to use the most often out of anything. But let's cover the others. Maybe I have a planet like this. We're going to give this thing a radius of 6.4 times 10 to the 4th meters. Times 10 to the 6th meters. This is the radius of the Earth. We'll give this thing a mass of 6 times 10 to the 24th kilograms. And maybe I want to know the potential energy when I am let's go 1,000 kilometers off the surface. So I'm going to find a spot here and say I am 1,000 kilometers off the surface. Let me find my potential energy. So what I need for this is the distance from the center of the Earth to that location. That's going to be, if I call this thing kind of my h, that's going to be r plus h equals the distance from the center. So 6.4 times 10 to the 6th meters plus 1,000 kilometers, so 1,000 times 10 to the 3rd meters, which is the same as 1 times 10 to the 6th, equals 7.4 times 10 to the 6th meters. And then I just have to plug in. My potential energy is going to be negative g m over r, so negative 6.67 times 10 to the negative 11th Newton meter squared per per kilogram squared. Mass of the Earth, that's going to be my 6 times 10 to the 24th meters. I need a mass for the object that I put here. So if I say this is a satellite with a mass of, let's go 1,500 kilograms, then that's what's going to go here. 1,500 kilograms. And then I'm going to divide by r. And when I do all of that, I get a final answer of negative 8.1 times 10 to the 10th joules, which is a lot. Maybe I want to know how this changes when I get down to the surface of the Earth. So when I get down to the surface of the Earth, I'm going to plug in very much the same way. I'm going to go negative g m over r. So there's g, Newton meter squared per kilogram squared. Mass of the Earth, mass of my satellite, distance from the center of the planet. When I do that, I get negative 9.4 times 10 to the 10th joules. Which, yes, it's a bigger number, but it's a bigger, more negative number, right? If we're looking at that potential well, where this is R, this is my potential energy. I was at an R value of 7.4 times 10 to the 6th, which is maybe here. I had a potential energy like this. Now, as I get closer, I get a potential energy that's lower, and that stays in form with the kind of potential energy well that we were expecting to get. So my change in potential energy, which is PE final minus PE, is going to be negative 1.3 times 10 to the 10th joules. It looks like my number is going up, but it's becoming more negative. I should be decreasing potential energy as I get closer to the surface. And I am. Last one, I told you that we would do a spring. Here comes a spring. So if I have a spring like this, and here is my equilibrium position, I'm going to put a mass of 5 kilograms, and I'll make this a weak spring. We'll go 200 newtons per meter. I will say that I have stretched this thing some distance of, let's go 10 centimeters. And I want to find my potential energy. My potential energy is half kx squared. So I get a half times my 200 newtons per meter times my x, which is the distance from equilibrium, so 10 centimeters, 0.1 meters squared. Half of 200, that's 100. 0.1 squared is 0.01. 100 times 0.01, that is 1 joule. I didn't need the mass because the mass isn't what determines the potential energy. Let's say I want to find how the energy has changed when I instead have this thing compressed by 1 centimeter. So now my potential energy, still half kx squared. So still half times my 200 newtons per meter. Now I am compressed, so I can put in negative 0.01 meters. The negative part doesn't actually matter because I'm going to square it, and that's going to come out positive anyway. So when I do this, I get 0.01 joules, still positive. Because I'm putting in a k, which is always positive, and I'm squaring x, I'm going to always get a positive potential energy with a spring, or 0 if I'm at equilibrium. So my change in potential energy is PE final minus PE initial. 0.01 minus 1 is negative 0.99 joules. There's an example with all three types of potential energy that I'm going to really be working with in this course.